Alright, now let's move on to looking at reflections where the electromagnetic field or the electromagnetic waves are coming from a dielectric medium, a perfect dielectric, but the boundary or the interface is a perfect conductor, right. So, this is slightly different, mainly because the boundary conditions that we will use in order to estimate the reflected fields are minorly modified, right. So, remember that we have 4 boundary conditions. In the case of purely dielectric media, it didn't matter, right, which boundary conditions you chose. We chose ones that were convenient for us since the interface charges and the interface surface current densities were 0. Right? But in the case of a perfect conductor, we know for a fact that it can support surface charges and it can also have surface currents, right. So, we will ensure that we try to sidestep any boundary conditions that involve us to know what the surface charge and the surface current densities are. Not that it is a mistake in using those boundary conditions, because in essence, once an electromagnetic field interacts with the perfect conductor, you should know what is the surface charge and the surface current. You can extract it from the given situation, but nonetheless we try to take some convenient boundary conditions. For example, we have no fields inside a perfect conductor, right. Okay, so we have no fields, right. So be it tangential or normal, we don't have any electric or magnetic fields inside the perfect electrical conductor. So we go with the same reference frame. So since the electromagnetic fields cannot penetrate into the conductor, one can quite surely at least guess that all of the incident power is basically reflected back. So let us look at the case of TE or perpendicular polarization. Okay. So quickly writing down the expressions for the incident and reflected fields, we have EI is E0, EY cap, e to the minus j kxi x, e to the minus j kzi z. Magnitude, direction, spatial variation and temporal variation we are ignoring. So Hi is E naught by eta minus cos theta I Ex plus sin theta I Ez and the spatial variation term. Okay. So Er is E0R Ui kxr x e to the minus plus jk zr z. right? And HR is E0R by eta. We have cos theta r Ex plus sin theta r Ez. Okay, so I'm kind of going through this fairly quickly because you should be fairly well adjusted to be able to write these expressions quite quickly, right? So both of these etas are the same. It is that corresponding to the parameters on region 1, right? So eta 1 is just square root of mu 1 over epsilon. Okay, so we are going to take the boundary conditions where we equate to 0, right? That seems to be more right. So we cannot have any tangential electric fields just above a perfect electric conductor, right? Similarly, we can also say the normal component of the magnetic field is also 0, right? We don't look at the other counterpart, right? So we don't look at electric field that is normal, or we don't look at the magnetic field that is tangential or parallel to the boundary, right? Mainly because these two fields can be non-zero, right? Because the perfect electric conductor can sustain or can hold a surface charge or a surface current. But for the case of the perpendicular electric field polarization, E normal is 0 anyway, right? So that boundary condition is not going to yield us any new information. It's just going to say 0 plus 0 is 0. So in this case, all of the electric field is parallel to the boundary or tangential. So from 1 E naught e to the minus j kxi x plus E0 r e to the minus j kxr x is equal to 0. So we again come up with the same phase matching relation, right? So kxi has to be kxr, which implies theta I equals theta r, right? If it were to be satisfied for all x's, right? And so this simplifies to simply E naught plus E naught r equals 0, which is to say E naught r by E naught is equal to minus 1. Okay, so in this case the field reflection coefficient is minus 1. Okay, so if I were to look at the total field in medium 1 or region 1, I can simply say that E total is E incident plus E reflected. Okay, but now we can make use of the knowledge we have regarding the field amplitudes. So this is E naught Ey e to the minus j kxi x e to the minus j kzi z minus E naught, right? The amplitude of the reflected field is minus E naught Ey since kxi is equal to kxr, we can say that this is e to the minus j kxix and e to the plus j kzi z. Why do I say kzi? Again, the k vectors in medium 1 is the same for the incident and reflected plane waves. So if kx component is the same, then kz component also has to be the same. Okay, so we can take the common factors and we see that we get a minus 2j sine kzi z. Okay, so if I were to plot this, so we can either say it is Ey, right, which is also the magnitude of the entire electric field vector, right. This is the perpendicular polarization. All of the electric field is in the y direction. So if I were to take the modulus of E total, right, so this is E total, I notice that for z equals 0, the field is 0, right. This makes perfect sense, right. We just said that the boundary condition is that E tangential is 0, right. So the reflected wave's electric field changes orientation, right, so as to perfectly cancel the electric field caused due to the incident wave. And since we are taking the modulus, we essentially hope to see a rise and fall of the electric field. Okay, but the difference between the case of total internal reflection with pure dielectrics and the case of a perfect conductor is the boundary itself is one of the nulls, right. The peak value that it reaches is 2 E naught. Okay, and the distance between two maxima or two minima is essentially pi over kzi, right, which is k cos theta I. Right. So if I were to say that k is 2 pi by lambda, right, so we can say for medium 1 it's subscript 1. So this same distance translates to lambda 1 over 2 cos theta I. Right, so the spacing between two nulls or the spacing between two maximas in the standing wave that we have generated is lambda by 2 cos theta I. So it seems to be a function of the incident angle, right. So when cos theta I is 1, right, or normal incidence, it is half the wavelength in the medium. And as you keep tilting it away from the normal for larger and larger theta i's, you notice that the nulls are separating, right, because cos theta I keeps decreasing, the space between the nulls increases. So what can we comment about H? But remember, H has both the x component and the z component. But nevertheless, we can always write that the net magnetic field is the sum total of the fields caused from the incident and the reflected waves. Okay. So you can always look back. I am just writing it down from my notes. You can go back to your notes or the previous slide and you should get this kind of an expression. Again, this is after making use of the relations that kxi is equal to kxr, right, and kzi is equal to kzr. This is the x component. Then we have sine theta I. Okay, so we can perform the same trick, right, and we can say that this is simply okay. For those who are following along with their own derivations, which I highly recommend, you can just compare your expressions with mine. We are again using the same Euler's expression to go from e to the exponentials to the rectangular form of cos theta I plus j sin theta I. Okay, so if I were to draw the same, this time I'd like to draw both hx total and hz, right. So what can you predict for hz? It's going to also be 0, right, because hz is the normal component of the magnetic field and that has to go to 0 at the boundary, right. So we get a very similar shape as in the electric field for hz as well, right. But surprisingly, hx is a function of kziz through a cosine function, right. Right. So remember that both the electric field and the z component of the magnetic field have a sine kziz, whereas the x component of the magnetic field has a cosine kziz, right? Which is to say that it actually peaks right. So it peaks where the normal component goes to 0. Right, which is totally fine. At the boundary, I can have tangential components for my magnetic field. In fact, this value of the magnetic field at the boundary near the perfect conductor is in fact going to tell us what the surface current density in the conductor is going to be, right. So, you can use the boundary conditions that we derived for perfect conductors, and based on the magnetic field intensity at the conductor boundary, you can actually estimate the surface current density, right. So, the peak value for Hx is 2 E naught by eta 1 sin theta I. Sorry, this is cos theta I. Okay, and the peak value here okay. So, if I were to ask you questions like what is the surface current density on the perfect conductor in the case of an electromagnetic wave incident at some arbitrary angle, you should be able to essentially get the boundary value for your magnetic field, and you can use the boundary condition to tell me what is the surface current density, right. So, again similarly in the case of say the parallel polarization, where the electric field now is in the plane of incidence, you will find that there will be a component of the electric field that is normal to the perfect conductor, and once the surface charges are set up, that you can have an appropriate boundary condition that relates the net normal component of the electric field to the surface charges, and you can estimate the surface charges as well, right. So, we are actually winding down this unit finally, but before we depart from this unit and enter the next unit, we would like to make a very short observation on the field intensity profiles upon reflection on this perfect conductor, right. So, we noticed for the case of perpendicular polarization, the E total had this kind of a cosine function, right. And this distance was lambda by 2 cos theta I. Okay. So, now we observe that if I were to insert an infinitesimally thin, right, perfect electrical conductor, right, at the null location, right, I notice that the solution should not be perturbed, right, because I am placing the perfect electrical conductor at the location where the field is 0, right. So, the boundary conditions are satisfied naturally. So, if I were to have such a geometry, it looks like whatever solution I have created for just a plane wave interacting with the perfect conductor stays as is, right. So, the Maxwell's equations should accept that this is a solution for the electric and magnetic fields, even in the situation when I have placed two perfectly electrical conductors facing each other, placed at a very specific distance apart from each other, right. So, in the case of the plane wave reflecting off of a perfectly electrical conductor, right, we notice that there is no power flow in the z direction, right. The power is actually being bounced back, right, in some sense, but there is a net power flow in the positive x direction, right. So, this is testament from the fact that we always have the e to the minus j k x I x, right. So, that along with the e to the j omega t is going to show us that there is a propagating wave, right, that is going in the positive x direction, right. So, if I were to combine these two ideas, right, that there is a net power flow in the positive x direction, and that if I were to place a second perfectly electrical conductor a certain very specific distance away of lambda by 2 cos theta I can actually have a very well defined power flow in the positive x direction, right, a confined power flow, which essentially can be thought of as continuously bouncing between the walls, right. So, I can have a sustained power flow in the positive x direction, right. So, this is what we call a waveguiding structure, right. So, it is sort of guiding the electromagnetic wave to move in the positive x direction, right. So, by clever placement of these perfect electrical conductors and launching the angle based on the distance between the two conductors, right, I can have a certain sustained power flow of electromagnetic energy in the positive x direction, right. So, this is what we call a waveguiding structure. We look at this in more detail starting from next week. Okay, thank you.